Welcome to Study Loop.
In each part of this problem, we are given an overall chemical reaction, and we want to determine what the overall change in enthalpy, or delta H of reaction, is. We want to calculate this in two different ways. In the first way, we are going to list out the formation reactions of each chemical species involved in the overall reaction from their respective elements. We are then going to determine the delta H of formation values for each one of these, and then combine the thermochemical equations using Hess's law in order to solve for the overall change in enthalpy of the given reaction. And the second way that we are going to solve for this to check our work and verify our solution is to use the overall delta H of reaction equation that involves the enthalpy of formation values. So we start with part A, and we first write out the thermochemical equations that correspond to the overall reaction given in part A. We write out the formation reaction for each of the chemical species involved in the overall reaction, and we start with CaCO3, and we see that we need calcium, carbon, and oxygen to form CaCO3. So for the formation reactions, the reactant side is going to be elements that occur naturally and do not require any energy in order to form. So that would be solid metals like calcium and carbon, and diatomic gases like oxygen. For all of these thermochemical enthalpy of formation reactions, we are producing 1 mole of the desired compound. So we therefore have to adjust the stoichiometric coefficients of the elements on the left side so that we can produce 1 mole of the desired product when we balance the equation. And that is why, for example, we use fractions for 3/2 oxygen so that there are 3 oxygens on each side of this reaction. We move on to the next reaction, calcium oxide, which is formed from calcium and oxygen. And so we have solid calcium and diatomic oxygen forming 1 mole of calcium oxide, and we balance it appropriately. And finally, for carbon dioxide, this is formed from the elements of carbon and oxygen. So that's solid carbon and diatomic oxygen to form 1 mole of carbon dioxide. Next, we can look up what the enthalpy of formation values are for each one of these thermochemical equations in the appendix or through some other appropriate source. And now we need to use Hess's law to combine these 3 formation reactions in order to determine what the delta H is of the given reaction. If we compare the given reaction to the formation reactions, we see that 1 mole of calcium carbonate is a reactant in the desired reaction and a product in the formation reaction. So we therefore need to flip the first reaction by multiplying it by -1 so that we can get CaCO3 to be a reactant instead of a product. If we go through the other chemical species, we see that 1 mole of CaO and 1 mole of CO2 are produced. And that is also the case for these formation reactions where you have 1 mole of each one of those species being produced. So now we manipulate those equations in that way, where we flip the first reaction and keep the second and third reactions as they are. And when we flip that first reaction, we multiply the delta H value by -1 so that it becomes positive. The delta H of formation values are given in units of kilojoules per mole, but for all of these formation reactions, we are forming 1 mole of each desired product. And so therefore, we can say that this corresponds to units of kilojoules or overall energy for each one of these. Now we have to cancel out like terms. We see that we have 1/2 plus 1, so 1.5 moles of oxygen on this side to cancel out with 1.5 moles of oxygen on the products. We also have 1 mole of solid carbon on each side and 1 mole of solid calcium on each side. And so when we cross that all out and we combine these three reactions, we see that we are left with the overall desired reaction. And so now that all we have to do to find the delta H of the reaction is to add these three terms together. And we should get an answer of delta H of reaction to be 179.2 kilojoules. The second way that we are going to determine this is using the enthalpy of reaction equation from the enthalpies of formation. So we subtract the reactants from the products. That is the enthalpies of the overall enthalpy change of the products minus the overall enthalpy change of the reactants. We need to multiply the number of moles of each species by their respective enthalpies of formation, so that when we cancel out the units, the moles cancel out and we are left in units of energy, kilojoules. So just looking at the reaction, we see that we have 1 mole of each chemical species, and we use the delta H of formation values and multiply them together and to get, for the product side, where we have CaO and CO2, to be a value of negative 1028.4. For the reactant side, we have 1 mole of CaO, and multiplying that by its delta H of formation value, we get that same value. And now we just subtract that delta H of the reactants from the delta H of the products to get the delta H of the overall reaction. We notice that that corresponds to the same value that we got the other way, 179.2 kilojoules. And so that is why that appropriately verifies our work, and that means that we calculated the correct delta H value both ways, since we got the same answer. That's the same process that we used for parts B and C of this problem. So again, we're forming calcium hydroxide from calcium, oxygen, and hydrogen, and balancing out appropriately to produce 1 mole. And we do that for the other two reactions, for CaO and H2O, those formation reactions. And we can look up the values for delta H again. And then we use Hess's law to combine those thermochemical reactions, because we see that we need 1 mole of CaO in the products, and that is present in reaction B. We need 1 mole of H2O in the products, which is present in reactant C, and we need 1 mole of CaOH2 in the reactants, but we need to flip the first reaction in order to move that from the product side to the reactant side. So we manipulate those equations in this way. We see we have 1/2 plus 1/2, so 1 oxygen on the reactant side and 1 on the product side. We have 1 mole of H2 on each side, and we have 1 mole of solid calcium on each side. We multiply that delta H of formation by -1 for the first reaction, since we flipped it, and we add it all together and get a final answer of 106.5 kilojoules for the overall enthalpy change for this desired reaction that we can form after using Hess's law. We then use the enthalpy of reaction from enthalpy of formation equation to see that we again have 1 mole of each chemical species, and we multiply it by the delta H of formation value for each one of those species, and do the total enthalpy change of the products minus the total enthalpy change of the reactants. When we do that, we see that we get the same value for delta H to be 106.5 kilojoules for part B. Finally, in part C, we have our given chemical reaction, and we form 1 mole of each chemical species in this way, but we do not have a reaction for solid iron, since it occurs naturally and has a delta H of formation value of 0. we look up the delta H of formation values for the other thermochemical equations, and then we combine them as we did before using Hess's law. You see that we have 3 moles of oxygen on each side when we add 3 halves twice on the product side, and 3 moles of solid carbon cancel out on each side. And when we combine all of those together, we have to multiply each of the given delta H values by the factor by which we flipped and manipulated those equations. So we multiply the first one by -1, second one by -3, and the third one by 3. And the reason that we use those coefficients is because we know that we need 1 mole of Fe2O3 as a reactant, but it is formed as 1 mole of a product, so we have to flip the first reaction by -1. And for 3 COs in the reactant side, we see that we need to flip this reaction and multiply it by 3 so that we have 3 COs in the reactant side. And then for 3 CO2, we have CO2 as a product, but we need to multiply it by 3 for that stoichiometric coefficient. So when we do all of that and we adjust the values for delta H, when we add them all together, we get a final answer of -24.8 kilojoules for the overall enthalpy change for the reaction in part C. And then again, we just need to verify that using the equation again for the total enthalpy change of the products minus the total enthalpy change of the reactants. And we use the stoichiometric coefficients to see we have 3 moles of CO2 in the products, multiply it by its delta H of formation to get that value. Then for the reactants, 1 mole of Fe2O3 and 3 moles of CO. We multiply them by their respective delta H of formation values and add them together. Again, we do not pay attention to solid iron since it has a delta H of formation value of 0. When we do the total enthalpy change of the products minus the reactants, we get an answer of -24.8 kilojoules, which again matches what we calculated before by combining the thermochemical equations.